Alrighty, so this is the same problem, example 7, but we've got a second part to it. And it says, consider the same problem above. How fast is the angle of elevation of the camera changing at that moment when the shuttle is 4,000 feet high? Okay, so if we draw this picture here again, we've got the shuttle, right? Launch pad. This is 3,000 feet. That camera is here. Okay, this is our D, right? And our shuttle actually shot up here, so this is our Y. Okay. Now, the angle of elevation, this goes back to pre-calc, okay? But the angle of elevation when from down looking up is going to be right here, right? Okay. So we still approach this the same way. We're just using our math skills here, okay? So let's think about this. What are we given? And we're still with a triangle, obviously. So what are we given? Well, we're still given what we started with, right? The dy dt. So we know that dy dt is 800 feet per second, okay? And I want to find, okay, how fast the angle of elevation is changing, okay? That means that I want to find the change of this, right, with respect to time. So the change of theta, the derivative of theta with respect to time. That's what I want to find, okay? And then I want to find it when y equals that 4,000, okay? So I could have put that in my given. I probably should have. That should go up there, okay? And then let's think about what equations do we know that can relate all of our variables together. So what can relate this with this, maybe? And since D we don't have, let's focus on this 3,000, okay? What can relate these things together? Well, it's a right triangle, so we can use some trig here. And I know that this angle, in relation to this reference angle, we've got our opposite side and our adjacent side, okay? So if I set up a ratio here, it's going to be trying to figure out an equation that's relating these two. Opposite, adjacent, I should immediately think tan of theta is going to give me opposite y divided by my adjacent side, which is 3,000, okay? But what I'm looking for is d theta dt, not theta, okay? So I need to find the derivative, right? And now it's not as bad as you think because we can just take these implicitly. So the derivative of tan of theta is secant squared of theta, but again, respect to time. So chain rule the derivative of theta with respect to time. Once we do that is d theta dt, and that's where our variable finally appears that we're going to be solving for. And then equals, well, you can just rewrite this just so you guys can see as 1 over 3,000 times y, right? So when you actually take the derivative of this side, you get the coefficient in front of it using that power rule. So it should be 1 over 3,000. But again, it's always with respect to time. So derivative of 1/3000th y is 1/3000th times dy dt. Okay, sweet. Now we have this formula, okay? But what we don't have is theta, okay? We're looking for this, and we have dy dt that was given to us. How are we going to find theta? Now, in this problem part up here, we found our missing, I forget where I did the work on a separate sheet of paper, but we found our d variable by doing, right, the Pythagorean theorem. So what can we use here to find theta? If I have a triangle, okay, I can use some trig, right? And so what was originally given to us was 5,000, right? Up here, that's what we found in that last problem. We found our d to be 5,000 when our y was 4,000, okay? Now, you have all the sides, so it doesn't matter what trig ratio you use to find theta, but I'm going to do this down here. Let's just say, okay, opposite, adjacent, right? So tangent, since we already had that set up, of theta equals opposite, well, 4,000 over my adjacent side of 3,000. Okay. And so if I go ahead and find this angle, right? You can cancel those out and just take the inverse tan of 4/3. And that's going to be theta. So with that, I'm ready to plug in everything. So I'm just going to do it up here. Secant squared of this inverse tan of 4/3. And again, you could have used any trig ratio. It didn't have to be the tangent one. Okay, of 4/3 times what I'm looking for, d theta dt, okay, is going to equal 1/3000 times dy dt, which they gave us as 800. Okay. All right, cool. So I'm going to calculate this in a step by step. So this is going to be secant squared. And then if you do the inverse tan of 4/3, make sure your calculator is in radian mode. Okay, because we want to keep things in radians. In calculus, we tend to work more in radians than with anything else, rather than degrees. Okay. So I'm going to just estimate this, that we got on our calculator, times d theta dt is going to be 800 basically divided by 3,000, which as a fraction will keep it as 4/15. Okay. And then this is just a number, right? So I'm going to divide it and get d theta dt equals 4/15 all over secant squared of 0.9273, which really, since we don't have secant on our calculator, I can bring that up to the numerator as cosine squared. Okay. And so really this is just going to be our d theta dt. And I should get, let's see, 4/15 times cosine of this number here, all squared, close parenthesis. And just so you guys can see in my calculator what I did here is I tried to take the exact value, but either way, we're still doing the same thing. And what you should get here is 0.096. Okay. And that's going to be in radians per second. Okay. Instead of degrees per second. All right. There we are. Okay. So again, this is example part 2 of example 7.